Okay, AP Calculus. I am Mr. McColley. This is the presentation for section 5.5. To keep it short, let's jump right in. First of all, you will see that my notes are in fact loaded up for this section. If you want to use the notes to follow along, go ahead and download those and print those off on your own. Let's jump right into it. So today, Section 5.5, we're going to talk about defining exponential functions with bases other than e. We're going to differentiate and integrate those functions, and then we're going to use exponential models to model compound interest and exponential growth. So you're going to see a lot of topics that come up in Algebra 2 and Pre-Calculus, and then we're also going to talk about them in terms of differentiation, so rates of change. All right, so some quick review things before we get started. First, a couple of properties of exponents. Anything to the 0 power is 1, except for when a is here. This a is equal to 0, 0 to the 0, 0. But anything other than 0 to the 0 power is 1. And the product of two exponentials of the same base, if I go a to the x times a to the x, is the same as a to the x plus y. The quotient, remember, if you have a to the x over a to the y, same base, you can subtract. And then exponent raised to an exponent, power to a power, you multiply. And then this one looks a little bit different, but you'll see why it's this way here in a little bit. But when I show you the differential rule on the next page, or the derivative rule on the next page, but the change of base formula, if you have log of some base other than log base 10 or log base e, which is ln, you can rewrite that as 1 over the log or the ln of whatever that base is times the ln of whatever you have there. So we did those in Algebra 2, we did those in Pre-Calculus, so those shouldn't be that new. The things that are new are these differential rules. So if you're taking the derivative of some exponential with some number other than e, it's just going to be the ln of whatever that base is times that exponential again, so a to the x. If you this is the chain rule example for this. So if you go the derivative of a to some expression that's in terms of x, it's still the ln of a times that exponential again times the derivative of whatever that composed function in the exponent is. Similarly, for logarithms of other bases, it's going to be the derivative of log base a of x is going to be 1 over the ln of a times x. And again, that comes from this expression right here, ln of a. If a is a known number, that's a constant, so you just leave it, and the derivative of ln x is just 1 over x. So that's how they get this thing. And again, the chain rule form of that differential rule is the logarithm of, or the log base a of whatever composed function you have in there will be 1 over the ln of a times that composed function times the derivative of that function. Just a real quick review so you see them and you have them down when you come to them in the problems over the practice work. The compound interest equation, a equals p times 1 plus r over n to the nt. Remember, let's get the right tool here. R is going to be the rate as a decimal, and n is the number of compounds, compounds per time period. And t is the time period. And let's see, did I have anything else? P is the principal. That's principal. He's your friend. The principal is the initial amount. And the A, that will be our final amount. So again, things that you've already seen. And then the definition of exponential function to a base, a to the x is equal e to the ln of a times x. And again, this shouldn't be new. These are all expressions that you've seen. And we can use this rule to do an integration, or we can say, excuse me, that the integral of a to the x dx is 1 over the ln of a times a to the x plus some constant c. All right, so I went through that rather quickly. I am going to refer to these differentiation rules quite a bit here as we move forward. But I thought we'd start off with one of the review exercises, really the first half of the practice work, excuse me, is review exercises. So I thought we'd start with number 26 there on page 368, and it is this one. It is 5 to the 6x is equal to 8320. Now we're going to use quite a few of these rules here. But first, the first rule that we're going to use, we're going to use the exponential rules from a previous video, where I'm going to say, all right, I'm going to take the ln of both sides. So the ln of 6x equals the ln of 8320. Since I've taken the ln of both sides, I haven't changed the problem. And since whatever I did to the left or did to the right keeps it balanced, but the property of logarithms says that I can take this exponent and move it down. That'll give me 6x times the ln of 5 equals the ln of 8320. And then I'm going to divide both sides by 6 ln 5, divide by 6 ln 5, and that'll give me x, and that'll be equal to, and we'll just go grab a calculator real quick, clear out the noise, and then we started with the ln of, forgot already, 8320. So 8320, close that parenthesis, divided by, open the parenthesis, 6, and then it was ln 5, close the parenthesis twice just to make sure. Let's check. I think I have all of the values. 320, that's what I want. Hit enter, and that is going to be 0.935. We'll make sure we round to 3 decimal places. 0.935. Okay. So again, that's pretty much a review problem. This is pre-calculus. And we did quite a few problems like that. Let's move on to the calculus. So in page 368, number 42, they ask us to do the derivative of, so they give us f of x is equal to 3 to the 2x. And I thought I'd start with an easy one. Looking at this, I have a value a to some expression that's in terms of x, and so I'm using this chain rule form of this derivative rule. And so what we're going to do is we're going to take the ln of whatever that base is times that whole function again, times the derivative of that function. So going back to this one, f prime of x is going to be the ln of the base, and that's 3. And then we're going to multiply that times the entire expression again, so 3 to the 2x. And then we're going to multiply that by the derivative of that expression. So I put in 2. And really this is good, but you might go 2 ln 3 times 3 to the 2x. Got that. All right, moving on. Had a blank one in there. So number 56, if you look at number 56, it says f of x is equal to, let's see here, log base 2 of the third root of 2x plus 1. Now in the directions it says find the first derivative, but you may want to apply some logarithmic properties before differentiating. And the reason that I'm going to do some messing with this before I actually do the derivative is really I have the composition of 3 functions. I have the composition of log base 2 of x, I have the function third root of x, and I have 2x plus 1. So there's 3 compositions in there, and if I really wanted to do this correctly, I would have to do the chain rule. So what I'm going to do is I'm going to rewrite before I go any further. I'm going to change this. I'm going to say log base 2 of 2x plus 1 to the 1/3. So change the radical to a rational exponent, and then we're going to use the rule that we used in the first problem that says if you have a logarithm, you can take any exponent and move it down. So now I've got 1/3 log base 2 of 2x plus 1. And what that does for me is it allows me to treat that as a constant. So just like when we did f of x equals 3x to the 4th, when I do the derivative of this, I just leave that constant alone out front. So the first derivative of that is 3 times 4 and then x to the 3rd, giving us that, which we basically do in our heads, 12x to the 3rd. I'm going to do that with that constant now. So now I go back to those rules and notice again, I have the chain rule, I have this composition of functions, I've got log base whatever times some function. So it's going to be 1 over the ln of that base. So in the one that we have here, it'll be 1/3, we leave it alone, and then it is the 1 over the ln of whatever that base is. In this case it was 2. And then, look at this, times whatever that thing is. So in this one we had, I'm going to extend it, 2x plus 1, so I've got 2x plus 1, and then we multiply that by the derivative of whatever that u is, which is just going to be 2. So I end up with 2 over 3 ln times 2 times 2x plus 1. All right. And we're doing real well for time. I know I kind of went fast, but you guys can hit pause and go back. And if you have questions, just leave a comment. And so my last one for today is 78. And number 78, it says find the integral of x to the 3rd plus 3 to the negative x, puts it in parentheses, puts my dx here. Now, this is the sum of 2 separate functions. So I'm going to separate them. I'm going to go the integral of x to the 3rd plus, or you know what, let's make it look nice, x to the 3rd dx, and then plus the integral of 3 to the negative x dx. Now this integral we've been doing. It's no sweat. It's just a simple power rule. We say, all right, it's going to be x to the 4th over 4, which is what we have done before, plus. Now, this one, this portion, or this derivative, is part of the new information. So if I go back up to, let's see, where did that go off to? There you are. So the integral of any base to the x power is going to be 1 over the ln of that times that base again plus c. So let's go back down to here. We'll have 1 over the ln of the base, which is 3, times that expression again, times the derivative of that, which would be, or the derivative of x, which would be -1, plus some constant c. And so our final expression, x to the 4th all over 4 plus, actually, you know what, we'll take that negative there and we'll incorporate it into our final answer. Instead of a plus, we'll have a minus. We'll have 3 to the negative x. And you know what? We have a negative x. Let's get rid of our negative exponent and push that back down to the bottom. So we'll have 1 over the ln of 3 times 3 to the positive x plus some constant c. I like that. That looks good. And that brings me to the end, and kept it right around 15 minutes. Not too bad for 4 examples. And again, folks, use stop, use pause, review, print out my notes, have all this stuff with you, go back, check it over, make sure I didn't make any mistakes. If you see any arithmetic errors, please feel free to leave me a comment. I'll see if I can't fix it. And just as one thing, once you've watched this video, leave your name and your favorite color. That's all all I want. If it was me, Nat McColley, purple. That's all I want to see. That way, let me know that you watched this video all the way to the end, and don't tell your classmates. We'll keep it our secret. All right, have a good day, and goodbye.